Good day, everyone. I am Christelle Cruz
And I'm Jahn Wilbert Carullo.
And I'm Jahn Mariz Villaruel
of Bachelor of Science in Computer Science, first year, Section B. And we are going to tackle about approximating the area under a curve.
Welcome to our video presentation on approximating the area under a curve. When we encounter a curve on a graph, we often want to understand the space it occupies, which is where area comes in. The concept isn't just about geometry. It is a powerful tool in fields like physics, economics, and engineering. In this presentation, we'll explore a fundamental method for approximating this area. Using rectangles, we'll delve into why we use this method, how it works, and its application. So let's dive in.
Today, I will illustrate the net of area from graphs. Supposedly, we have this graph. A is the area under the curve y is to 1 minus x squared and 0 is less than to x and less than to 1. In order for us to get the graph, we will use the left endpoint approximation. We will divide the interval 0 and 1 of the x-axis into 4 sub-intervals of equal lengths, which is 1 minus 0 divided by 4, it is equal to 1/4. So it means 0 is to 1/4, and 1/4 is to 1/2, and 1/2 is to 3/4, and 3/4 is to 1. With each length, 1/4, we can label the endpoints of these sub-intervals, as x of 0 is equal to 0x, of 1 equals to 1/4, x of 2 is equal to 2/4, and x of 3 is equal to 3/4, and x of 4 is equal to 1.
Today, we're diving into a fundamental concept in calculus, Riemann sums and regular partitions. When we're faced with the task of finding the area under a curve, we often turn to these methods. A Riemann sum is an approximation of the area under a curve by dividing the region into narrow rectangles and summing their areas. But to do this, we need to understand regular partitions, dividing the interval of the function into equal subintervals. These techniques are the building blocks of integral calculus, allowing us to handle complex shapes and real-world problems. Let's explore how Riemann sums and regular partitions work together to approximate areas under the curves. The example of getting the regular partitions and divisions into subintervals is already discussed earlier. This time, we are going to illustrate and discuss to you on how we can get the areas of each functions.
Since we get the 4 subintervals with equal length, now we will get the values of the function at the endpoints of each subintervals. For the left endpoints, we have x of 0 is to 0, x of 1 is to 1/4, and x of 2 is to 1/2, and x of 3 is to 3/4. That means the value of x is to 0 is 1, and x is to 1 is 15/16, and x of 2 is to 3/4, and x of 3 is to 7/16. On our side, you can see the formula to solve or to get the left endpoints approximation. Here we are going to add the value that we get from the y-axis, which are 1, 15/16, 3/4, and 7/16. We are going to multiply each value by 1/4. After getting the sum, which is 25/32, we are going to change it into decimal, which is 0.7813. Now, let's move on to the right endpoints approximation. Just like the left endpoints, we are going to add the value that we get from the y-axis, which is 15/16, 3/4, 7/16, and 0 by 1/4. After getting the sum, which is the 7/32, we are going to change it into this decimal, which is 0.531. For the midpoint, we are still going to multiply the area of x, which is 1/4, to each values, which are 2,461 over 2,500, 4,297 over 5,000, 3,047 over 5,000, and 293 over 1,250. The sum will be 6,719 over 10,000, and in decimal it is going to be 0.6719.
Let's determine the left, right, and midpoints and points for the function y is equal to 1 minus x squared over the interval of 0 and 1. Using Raymond's sum and create table for each function. Function is y equal 1 minus x squared over 0 and 1. The interval 0 and 1. Number of sub-interval is, let's consider dividing the interval into 4 equal sub-interval. Width of each sub-interval is delta x. Area of x equals 1 minus 0 divided by 4 is equal to 0.25. Left, right, and midpoint and points. Left endpoint x of I minus 1. For the left Riemann sum, we use the left endpoint of each subinterval as the sample point. Left endpoint for the I subinterval is x of I minus 1 is equals A, or area, plus I minus 1. See that delta x. Right endpoint x of I. For the right Riemann sum, we use the right endpoint of each subinterval as the sample point. Right endpoint for the I subinterval x of I equals A plus I. See that delta x. Midpoint fraction of x of y equal minus 1 plus x of I 2. For the midpoint Riemann sum, we use the midpoint of each subinterval as the sample point. Midpoint of the I subinterval fraction x of I minus 2 plus x of I equals 2. For the summary, left Riemann sum is equal 0.7813. For the right Riemann sum is equal to 0.5313. For the midpoint, Riemann sum is equal to 0.6719. The tables demonstrate the calculation of the left, right, and midpoint Riemann sum for the fraction y equals 1 minus x squared over the interval 0 and 1 with 4 equal subinterval. Each sum provides an approximation of the area under the curve using different sample within each subinterval.